So I'm going to be talking about entropy today, and in particular, I'm going to try to follow the description of entropy from the David Gaskell textbook. I think that in many regards he does a very good job introducing entropy from a macroscopic perspective. There are a few points, though, that I think need to be annotated in the book, and I'll point those out as we go. So basically, when we talk about entropy, we're talking about the concept of a spontaneous process. And a spontaneous process is one which happens without an external energy. So if you imagine, a system, and inside that closed, isolated system, you've got a plane, and you've got some brick on that plane. Well, if this is state 1, you can imagine a state 2 where it is moved slightly. And if this is flat, you know that it's not going to spontaneously move. These two states have the same energy, but it will not spontaneously occur. And in contrast, if you have a system like this, state 1, this will spontaneously shift at some time to state 2. And this is what we mean by spontaneous. To say that a process is spontaneous is also a way of saying that it is irreversible, or there is some component of this that is irreversible. You can imagine here that this can't be reversed without, taking your finger in the system and pushing it back up the hill. And this simple picture is the picture that we want to talk about. Now, when we discuss the reversibility, we're going to characterize that in terms of the entropy. And we use S2 minus S1 equals delta S, the change in the entropy. So if something's spontaneous, then there is a positive change in the entropy. And I'm going to say without proof that the change in the entropy is associated with a change in the heat of the system. And we scale that by the temperature which it occurs. There's a proof of this in Fermi's textbook, but here we're just going to move working from this definition. Now, the chemical system that we can picture is a chemical system in which we have a piston and it's some insulated piston like this. And in this piston system, we've got a plunger. And in this, we have liquid and vapor. The liquid and the vapor are, in equilibrium, and constantly you've got some liquid coming up and becoming vapor, and some vapor coming down and becoming liquid. With this vapor, there's a vapor pressure. And if this vapor is in equilibrium with outside, then the external pressure is equal to the vapor pressure and the system's in equilibrium. Now I drew this also to be able to add a thermal reservoir. Or a thermal heat bath. And that's at some constant temperature. And within this picture, you can imagine then that, if we depress this plunger, we change the pressure, we have condensation of vapor into liquid to reduce the pressure until the vapor pressure and the external pressure are constant, are equal. And for that to happen, there has to be also some thermal exchange between the heat bath. Now, this is the first point in the text that I think really needs a annotation. In the Gaskell text, he talks about changing the pressure by either depressing or extracting the plunger as delta P. And what's important here is this is a magnitude. It's not P equals the magnitude of P2 minus P1. It is not equal to P2 minus P1. The sign is always positive. And what's important about that is that through the rest of this discussion, we're going to have a positive or negative sign in front of this delta P that specifies if the pressure is increasing or decreasing. And I think, from my perspective, when we talk about thermodynamics from a chemistry perspective in general, when we talk about pressure, it's always a little bit challenging because the sign is different from stress and strain. So those of us interested in solids, you have to think about positive and negative signs. So let's say that we have this system, and we take this and we decrease the pressure. So we pull on the piston, pull out piston, and we pull out the piston so that a certain amount of liquid transforms into vapor, right? So this causes in P, and that's by negative dP, or delta P. And for a certain amount, let's say that 1 mole liquid transforms into vapor. So we know how some finite amount that occurs. Well, the work then is T minus delta P V. If, on the other hand, we had taken this and we had, once it's pulled out, we take and then we push the plunger in, and we do this until 1 mole of vapor transforms into 1 mole liquid. Well, then we're changing by some positive delta P, and the work call this work out. Call this work I for work in, to push the piston in, is equal to x plus delta P V and work tote is equal to P x plus delta P V minus P x minus delta P V is equal to 2 delta P V. The total work for taking the cylinder and pulling out and then pushing it back in. Now, in kind of our thought experiment, you can imagine, a plunger and liquid vapor. You can imagine that if you don't change this pressure, you don't apply extra pressure according to dP, if you don't do that, there will be no spontaneous change. So if this is zero, then nothing happens. So delta P drives the spontaneous change of state. So we kind of immediately have a way now of talking about kind of this spontaneous contribution and the irreversible contribution to the change of state. So, consider evaporation. That same system. Now, if it's pure reversible, then the work, and we're going to call this max, is equal to P E X T V. And that, and we're calling it maximum work because this is the maximum work. Well, you'll see where this comes from later. But nonetheless, it's just basically saying that the work that occurs is the pressure times the volume. And this notation bothers me a little bit because it's counter to what you may think of when you think about pressure volume work, because you expect to be some change in pressure. We are pretty much preconditioned from observing the world to expect a delta P. But let's just say that there is no change in pressure, but we still witness evaporation. Well, the work being done in this evaporation is PV. If irreversible, spontaneous, then the work is equal to PEXT minus delta P V. So here we're saying that our use of W is the work for an irreversible evaporation process. And that is equal to max minus delta PV. Remember again that we're putting our signs in to specify the direction, and delta P is just a magnitude. Also, it's worth noting that now we have this, if you want to think about this as the reversible work, and this being the difference. This is the irreversible. Gaskell doesn't use these terms, but I think that carrying these through the discussion is helpful. So we have some irreversible work. And similarly now we can talk about the heat. Now this system that we had, this ideal system, was insulated. And maybe I didn't specify that, but think of this as an entire system, the heat bath and the piston system being isolated. So our universe we think of as being an isolated closed system. We say there's nothing outside of the universe. So what we've created here essentially is a miniature universe, where the thermal bath is a universe, and this happens to be the a piston that is in thermal and mechanical contact with the universe. So that means that there's no change in energy of the system on the whole. So we can talk about work and heat being equal to each other. So if reversible, then we have some reversible heat change, which is equal to delta U plus W max. And this is the heat flows from bath into the system. So this W max, again, is our PXV. And this U is the system's change of energy. If it's irreversible, then we have Q, the heat that flows from the bath into the system, equal to delta U plus W is equal to delta U plus PEXT minus delta P V. So the important thing here is that this is equal to delta U plus W max minus delta PV. So that and that are the same, which means that Q is less than Q reversible. So it's saying that if the evaporation process occurs spontaneously because we pulled on the cylinder a little bit to decrease the pressure, the negative sign, then the heat that flows in to the system from the heat bath is less than if it were a purely reversible process. Now, the Gaskell textbook uses a term, and it's a common term. It bothers me a little bit because I think it's kind of, at least in from my perspective, is difficult to imagine, but they talk about mechanical energy being degraded into thermal energy. Max minus W. So here, maybe I'll write it here instead. They talk about max minus W equal to P X V minus P X minus delta P V is equal to delta P V, and they call this degraded mechanical energy. Now, and over here, I was referring to this as our irreversible work. What bothers me about this term is that students, and I know I personally did, thought about degraded mechanical energy. I said, well, that's just because we're not, we're pushing something and we don't have proper lubrication, or we're not being careful enough, and it's some just experimental vestige, and it is not exactly that. It's actually a little more fundamental than that, because anytime something occurs spontaneously, there must necessarily be degraded mechanical energy, and that's just a consequence of theory. But let's just make note that if we take these two, we get this delta PV. I'm calling this the irreversible work, and Gaskell is calling that the degraded mechanical energy. So if we want to talk about what's the difference what is difference between a reversible and irreversible? Well, we can talk about the difference in the heat. So we can say that Q rev minus Q, remember this is the change in heat, or the heat that flows into the system, if the evaporation occurs spontaneously without us changing the pressure. This is the change in heat if we apply a small pressure, we're pulling it, I guess. We pull on the piston a little bit, we reduce the pressure, and heat flows in. So that is equal to W max minus W. And that's because delta U system, or total, is equal to 0. The energy of the system changes, but the total, system plus bath, that's isolated, does not change. And this then is plus delta PV, right? Because we had max minus W, which was max minus delta PV. So cancel. This difference here, I've denoted this as Q irreversible. Again, this is not used in your textbook, but I think this is a handy way to think about it. And essentially, because I'm saying that our QIRR is equal to delta PV, and before I'd said WIRR is equal to negative delta PV, we are setting these two equal to each other, or with the change in sign. So this is also then verifying for us that Q rev is greater than Q. Which we'd already seen here. And what this means is that less heat is transferred when delta P applied. If you want to think of it, you can think that in the process of these expanding the system, we are getting thermal energy, this mechanical heat, and that mechanical heat is contributing to the evaporation, right? There has to be some energy absorbed by the molecules for them to go from being a liquid to a vapor. And that means that less heat has to be transferred into the system from the thermal bath. So to put this in terms of entropy, if pure reversible, meaning delta P is equal to 0, we're not applying any pressure to the piston, then delta S bath is equal to negative Q reversible over T. The system is equal to plus Q rev over T, and delta S tot is equal to delta S bath plus delta S system is equal to 0. So for a process that's reversible, we have this, you can imagine evaporation occurring without us applying a pressure. Then there's no change in entropy of our isolated system plus thermal bath. If, however, it's irreversible, then delta S bath is equal to negative Q over T, and that's the heat transferred into the system from the bath. And S system is equal to Q over T plus Q rev minus Q over T is equal to Q rev over T. we're basically saying here that the change in the heat is the change in heat needed for evaporation. Right? This is, you can also think of this as when I think of this term, you can think of this as Q rev minus Q rev plus Q irreversible, right? So that means that delta S tot is equal to delta S bath plus delta S system. Delta S tot is equal to negative Q over T plus Q over T is equal to Q rev minus Q over T. And because Q less than Q rev, delta S tot is greater than 0. So for this spontaneous process, delta S tot is larger than 0. And this is one of the conclusions coming from the discussion of the second law of thermodynamics, which we'll come back to. And it's also worth pointing out that this Q, if we think of it as Q rev plus Q irreversible, then that's going to give us the irreversible heat transferred in our entropy term. Now, if we want to reverse this process and then consider instead condensation, we can basically go through exactly the same derivation. The trick here is that now, so for example, delta S system is equal to negative Q reversible equals, say, over T. This is if reversible, and delta S tot is equal to 0 in that case. But the highlight here is that we've changed the signs. A place where this also comes into play is when we talk about work, right? We had our work terms here. So now these change because we're applying a positive pressure. We're compressing the gas to get condensation, which means that our Q reversible is equal to, so delta U plus max, and Q is equal to delta U plus W is equal to delta U plus W max plus delta PV. So we now have Q is greater than Q reversible. And our sign comes into play there. So writing out the, sorry, this is that's for irreversible, and that is for reversible. And what that means, it means that talking about the entropies, system is equal to negative Q over T plus Q minus Q reversible over T is equal to negative Q. Well, I'll come back to that. Notice here that we swap the order there because we had a change in sign. So instead of being reversible minus Q, we have now Q minus Q reversible. And delta S bath is equal to plus Q over T. So delta S tot is equal to negative Q over T plus Q minus Q reversible over T plus Q over T is equal to Q minus Q reversible over T. So this, you can think of this as delta S, the irreversible contribution to the entropy, and we had that in our expansion as well. And again, because Q is larger than Q reversible, remember we switched the signs on the delta P, then that means that delta S tot. So again, if spontaneous, regardless if it's going to be plus or minus delta P, then delta S tot is larger than 0. So to summarize, entropy comes from change in heat in all spontaneous processes. There exists a change in heat due to degraded mechanical processes, or call it just degraded processes. And as a result of this, there is always delta S tot greater than 0. So any spontaneous process will result in an increase in the entropy for for that little miniature universe we created. And that also means our universe, there is going to always be this increase in entropy. Now, entropy is a state function. So all of those great properties that we learned about when we talked about enthalpy and energy, etc., are the same. The difference with entropy is that entropy is not conserved. Right? It's always increasing. In our closed, isolated universe. And that makes it a little bit different. Something about it that is useful is that it means that if you have your dependent variables and you know that you can define the entropy between some, P1, P2, some S is a function of P1, P2, you're going to have some surface that you can think of as an isoentropic you can define an isoentropic surface. So every point on that surface is constant entropy. And you know that in principle, you can take and move to any point without changing the entropy, but it won't happen spontaneously. If, on the other hand, you have another surface which is higher, you can spontaneously transition from one entropy to a state in another system. So if S1, S2, S1 is always less than S2, that process is spontaneous. Going from the upper surface to the lower, that will not happen. At least not in a closed, isolated system. If you have some way to apply external energy, you can reach your hand into the glove box and then move things around, then it's possible to change that. So, thank you very much, and I will see you next lecture.